In this video, we will go over regression analysis, and the example I will be using is an ordinary linear regression using a single independent variable. This example question is from your textbook, which reads, a legal researcher wanted to measure the effect of length of a criminal trial on the length of jury deliberation. She observed in a sample of 10 randomly selected courtroom trials the following data on length of trial in days and length of jury deliberation in hours. So we have some data over here on the right. On X, we have the number of days that the trial lasted, and Y, we have how many hours the jury deliberation took after the trial. So we are being asked to do a couple different things: to draw a scatter plot of the data, draw the regression line on a scatter plot, calculate the regression slope and the y-intercept, predict the length of jury deliberation for a recently completed trial that lasted 6 days, and finally find the coefficients of determination and non-determination, and now really finally construct an analysis of variance table and perform an F-test. Wow, that's a lot to do, but you know what? We can do it. So the x-axis is home to the proposed independent variable, and the y-axis is for the dependent variable, or the variable that might change as a function of x. In this case, the hours of jury deliberation, y, might vary depending on the value of x, which is the length of the trial. The null hypothesis is that there is no relationship between length of criminal trial and the length of jury deliberation, and we're going to use an F statistic to find out if we should retain or reject the null. But I'm getting ahead of myself. Let's start by creating a scatter plot showing our data. I'm going to highlight the data first, and I'm going to include the X and Y as the labels for the data there. I'm going to click on Insert and select the charts that have the scatter. I'm going to select a simple scatter chart, and there we have it. I'm going to do some things to clean this up. First thing I'm going to do is get rid of the title because it really isn't helping us very much. The second thing I'm going to do is add axis titles. So here we go. And as I mentioned before, the x-axis is the independent variable of length of trial in days. And I said length of trial. That'd be a different thing altogether. All right. And our y-axis is length of deliberation in hours. All right. What I'm also going to do now is I'm going to make these data markers match our data. And they're actually pretty close, but sometimes you will do a scatter plot and you're going to wind up with weird ranges of data. So I'm just going to show you how to change it just so you have that information. So I clicked on the x-axis numbers. I'm going to click on Format Axis and Axis Options. I'm going to make my minimum 0 and my minimum 8. And that actually works pretty well because I think our maximum for x is 7. So we're going to keep that just the way it is. And then I will do the same for the y-axis. For the y-axis, our max is 12, so I'm just going to change the maximum to 13, just to keep it as tight as we can be. All right, so now I have a scatter plot that shows the data graphically, so we can look at that and make some conclusions. First of all, when we look at it, we can kind of see that there's a positive trend line going here. But what we're going to do right now is we're going to actually add a trend line. So I'm going to press on the plus symbol, click on trend line. And you can see that the best fit line does kind of fit straight through there. That's our trend line. I'm also going to click on trend line, and I'm going to go to more options, and I get the more options right over here. And you can see that we're working with a linear trend line. That's what our problem is. I'm also going to click on two things: display equation on the chart and display r-squared value on the chart. And these things are going to be very helpful to us as we do our own calculations. We can check them against these numbers, so that's kind of exciting. Okay, I've put our chart away for just the moment. It's there when we need it. So we're going to start by just looking at what the regression model is. And the regression model, we'll look at this formula here. It takes the form of y equals a plus b times x, where where a is the y-intercept, or the value of y, when x is 0. And b is the regression coefficient, or the slope of the line, which tells us how much y changes for each unit increase or decrease in x. So to make this a little bit more easy to understand, we're going to just start calculating our formulas. We're going to start by calculating our b. And as you can see right over here, the formula for b is simply the sum of the products of the deviations divided by the sum of the squared deviations. And these terms should be familiar from the video on correlation. And so let's go ahead and fill in this set of numbers over here, because that's going to help us to fill in everything that we're going to need. So the first thing I'm going to do is find my means. And simple enough, E equals formulas, insert function, average. And I'm going to select all these and hit return. So the mean for the number of days is 3. And I'm going to do average. And the mean for the number of hours is 5. Okay, so far so good. The next thing we do is take x minus the mean of x. So we have the first x minus mean of x. And if you will recall, since we're going to be subtracting all of our x's, the mean from all of our x's, we need to keep the mean constant. So we're going to put dollar signs around the b and the 20 in this case. Okay, and so drag that down. And as always, because I'm super compulsive, I need to make sure I did this right. So I'm going to insert the function. I'm going to sum up my deviations, and they should equal, what is it? 0. Yay, and they did. I'm going to do the same for y. Y equals the mean of y. Again, I need to put dollar signs because for every subtraction problem, I want the mean to be the second number. The mean of y. Okay, and I'm going to drag down. And here we go again. Whew, still 0. Great. We also need the sum of the products of the deviations. So that's equals the x deviation times the y deviation. And I'll drag that down. And then we finally need two more things, which is the x deviation squared and the y deviation squared. So equals x deviation squared. Drag it down. Oh, that's not going to work. And the y deviation squared. Okay, and finally I know I'm going to need the sum of these numbers, so I'm going to drag over the sum formula, and I end up with 33, 32, and 84 for my sums. And just because I like things neat and tidy, I'm going to make everything 2 decimal points, but it doesn't really matter. These are all whole numbers to begin with. So we move on. Now that we have all this information, we can plug this in to find our b. So let's do that right now. Equals the sum of products over, and this time it's just the sum of the x deviations. There we go. And I press return. And our b is 1.03. So the b is our slope of the line, and the slope is also referred to as the regression coefficient. So b is equal to the sum of the products divided by the sum of the squared x deviations. For every 1 unit of x, y will increase by 1.03 units. Okay, so next we'll figure out a, or what's called the y-intercept. And this is the expected score on y when x is 0. And this is also considered the baseline number in regression. And as you can see in the formula right here, it is figured by taking the mean of y and subtracting the b that we just found and multiplying that times the mean of x. So this gives us a y-intercept. So let's take a look at that. Equals the mean of y minus the b that we just found times our mean of x. And we end up with 1.91. So 1.91 is our expected y-score when x is 0, the y-intercept. So as you can see, these values, b equals 1.03 and a equals 1.91, are equal to these numbers that we found when we did our scatter plot. So it's a great way to check your answers right here. So we can use this equation as a prediction equation. So for example, for any value of x, we can predict the length of the jury deliberation. So in part D of this question up here, hold on, it's here somewhere. It says predict the length of jury deliberation for a recently completed trial that lasted 6 days. So let's do that right now. I'm going to plug in the regression model to find a predicted y-score for this. So here we go for a trial that lasted 6 days. So I'm going to use the regression model, and I'm going to enter our A first. So here's the regression model. A plus our B, and I'm going to multiply it, in this case, by 6, because this is a trial that lasted 6 days. So the predicted hours for a jury deliberation for a trial that lasted 6 days is 8.09 hours. So we can use this regression as a predictive model. When we know one score, we can predict the other. And in addition to finding predicted scores, we can utilize the correlation to determine a PRE measure, or what's called a proportionate reduction in error. And that will tell us how much of the variation in length of jury deliberation can be explained by the length of the trial. First, we can calculate the correlation between the days of the trial and the hours of deliberation. So I'm going to move this over just a tad so you can see some new formulas here. Okay, so we have the formula for Pearson's correlation right here, and we can easily figure that out. Let's plug that in. We've already used these terms before. So our Pearson's R is going to be equal to the sum of the products divided by the square root of the sum of the x deviations times the sum of the y deviations. Oh, I think I just forgot something, but I did end up with the correct R. I know this, I've done this before, so R in this case is equal to 0.64. That's an indication of the association between these two variables. And the next thing that we're going to do is we're going to find something called R squared. And R squared is actually what we consider our PRE measure. It's called the coefficient of determination, and it's easily found by just squaring R. So let's do that. Equals 64 squared. And we get something funky, but that's okay. Okay, so our R squared, or our coefficient of determination, is 0.41. And this tells us that 41% of the variance in jury deliberation time is due to the length of the trial. The remaining 59% is referred to as the coefficient of non-determination. And this is the amount of variation in our dependent variable that we can't explain with our independent variable. And we calculate the coefficient of non-determination simply by taking 1 minus our coefficient of determination. And there you can see is 0.59. So we calculate this very simply. You will notice that the R squared that we calculated is equal to the correlation of coefficient of determination that we found on our table. 0.405 is equal to our 0.41 that we found here. So again, making the scatter plot and selecting those options helps you to double check your answers. Okay, so we have some information now that's going to help us to figure out statistical significance of our association. To determine the significance of regression, we utilize the F statistic, which is the statistic that we've used previously in analysis of variance. And it turns out that this process is very similar to the analysis of variance. First, we calculate the sums of squares, and then we use those in conjunction with the degrees of freedom to calculate mean squares and then calculate an F statistic. And I have two formulas here that are going to help us to determine significance. We have the sum of squares for the regression, and we have sum of squares for the error. And these utilize the sum of squares of the y deviations, and we did figure them out over here already. We haven't used them yet, but we did figure them out. Those y deviations are going to help us to figure out this part of the equation. So let's do that right now. Our sum of squares for the regression is equal to our coefficient of determination, or r squared, times the sum of squares for y, squared deviations for y. So let's do that. Equals our r squared times the squared y deviations. And that gives us a sum of squares regression of 34.03. The formula for our sum of squares for error is our coefficient of non-determination times the y deviation summed up. So let's do that. Equals our coefficient of non-determination times our y deviations. And that gives us a sum of squares error of 49.97. And next we calculate our degrees of freedom. The degrees of freedom for the regression is always equal to 1. How easy is that? And the degrees of freedom for the error is going to be the n minus 10. In this case, we have 10 cases or 10 trials that we're looking at, minus 2. And so our degrees of freedom for the error are going to be 8. And just like we did with analysis of variance, the next step is to calculate our mean squares, which are simply our sum of squares divided by our degrees of freedom. Easy, easy. So here we go. We're on mean squares for regression is going to be equal to our sum of squares for regression over our degrees of freedom for regression. Boop. And mean squares for the error is going to be the sum of squares for error over the degrees of freedom for error. Boop, again. And so our the way we calculate f is again going to be quite like analysis of variance. We're going to just divide the mean square of the regression by the mean square of the error, and that gives us an observed f of 5.45. We can determine if this f is statistically significant by looking at our critical values of f at the 0.05 and 0.01 significance level table. And that's in Appendix C of your book. So the degrees of freedom we already talked about for the numerator is 1. For the denominator was 8. So our critical value for f is 5.32. So let's enter that here, 5.32. And now our last step is to compare if RF exceeds the critical value, which it does. So we can say that this relationship is significant at the 0.05 level. Usually the results of a significance test for regression are presented in an analysis of variance summary table, just like the one I've magically made appear right here. The totals are simply equal to the sum of the regressions and the error sum of squares and the sum of the degrees of freedom. So it's basically all the information here. We just enter it into the table, so it's easy to see where we got our numbers. So there you have it. To summarize, based on our data, we calculated a regression equation of y, which is the length of jury deliberations. We found it equal to 1.03 plus 1.90 times x, where x is the length of the criminal trial. And we also determined that the length of a trial accounts for 41% of the variation in length of jury deliberation. And we also found that this relationship was statistically significant. So working with regressions is really just a spin on other procedures you've used in this course. It's laborious, it's got a lot of steps, but it's nothing really new. So in addition to completing this practice assignment, I encourage you to take the practice items at the end of the chapter out for a little spin too, because just doing these problems helps the concepts to sink in just a little bit easier. So good luck, and let me know if you have questions.